And welcome to section 8.4, Rational Expressions. The objectives of this section: to simplify rational expressions and to multiply and divide rational expressions. Some vocabulary for this section: rational expression and simplest term. An essential understanding: you can use much of what you know about multiplying and dividing fractions to multiply and divide rational expressions. The expression 1 plus 1 over x in the solvent is equivalent to the rational expression x plus 1 over x. A rational expression is the quotient of two polynomials. You will find that at different times it's helpful to think of rational expressions as ratios, as fractions, or as quotients. So let's take another look at this equivalence here. 1 plus 1 over x equals x plus 1 over x. So consider this. 1 plus 1 over x can be rewritten as x over x plus 1 over x. Note that all I've done here is I rewrote 1 as x over x. Basically, I thought of 1 as being 1 over 1, and then I multiplied that by x over x. Remember, you can multiply numerator and denominator by the same thing and not change the value of the fraction, just the way it looks. So rewritten 1 as x over x, and then we still have the term plus 1 over x. Now we have a common denominator, so we can simply write the numerator as x plus 1 over the existing denominator, x. A rational expression is in simplest form if its numerator and denominator are polynomials that have no common divisors other than 1, meaning that we can't factor out a common factor and then reduce the fraction. You simplify a rational expression by dividing out the common factors in the numerator and denominator. Factoring the numerator and denominator will help you find the common divisors. Below are some examples of rational expressions that are in simplest form. Notice x plus 1 over x minus 1. We don't have any common factors in the numerator and denominator that can be reduced. For a moment, if you pretend that the x minus 1 denominator were an x plus 1, now we have matching binomials in the numerator and denominator that can be reduced. The next example, x squared plus 3x plus 2 over x plus 3, also in simplest form. Note that the numerator can be factored, and can be factored relatively easily. I'll do that now. And now, having set up our binomials and input the x's, the first terms, I'm searching for two constants that when multiplied equal 2 and when added equal 3. Well, I'm thinking 2 and 1. Plus 2 plus 1. So there's another way to write our numerator in its factored form. That will all be over x plus 3. Notice there's nothing to cancel. Our binomials don't match. We have nothing to reduce, so therefore the expression itself was in simplest form. Some examples of rational expressions that are not in simplest form. X over x squared. Notice that x over x squared can be rewritten as x over x times x, and therefore we do have a common factor that can be reduced, and this would simply equal 1 over x if we were writing in simplest form. Most often you don't need to write that out. I do that as an example of what's really going on here. We would just cross off or cancel out the numerator x and then the squared exponent to leave a 1 over x, and then most likely rewrite this way. The next example, 3 times the binomial x minus 3 over x minus 3. Well, that just equals 3. We can cancel out the binomials in the numerator and denominator and find 3 over 1, or just plain 3. And our final example of not in simplest form, x squared minus x minus 6 over x squared plus x minus 2. In order to determine if this is in simplest form, we should factor. And while most of you probably don't need me to walk you through this, I will quickly, just for review. To factor x squared minus x minus 6, we're now looking for constants that when multiplied equal negative 6, and when added together equal negative 1. 3 and 2 sound pretty good. If the 3 is negative and the 2 is positive, let's see what we get. Our first terms give us x squared. Our outer terms give us a plus 2x, but then immediately following our inner terms, yield minus 3x. So 2x minus 3x, sure enough, is negative x. And finally, our last terms, negative 3 times 2, minus 6, or negative 6. For the denominator, with the x's in place, now I'm thinking of two terms, two constants, that when multiplied equal negative 2, when added together equal 1. I'm thinking 2 and 1. Now, one of those will have to be negative, one will have to be positive, and we need a positive 1 in the end. So the 2 will need to be positive, x plus 2, and x minus 1. A quick check of FOIL, sure enough, brings us back to x squared plus x minus 2. And notice what we have going on here. We have a matching binomial in the numerator and denominator, which would cancel out, and we would find that this expression can be reduced and rewritten as simply x minus 3 over x minus 1. And that would be in simplest form. So we've considered rational expressions and their simplified versions, but in order for them to truly be equivalent, well, let me just read this. A rational expression and any simplified form must have the same domain in order to be equivalent. So that's worth taking note of. Take a look at this. We simplified on the previous slide x squared minus x minus 6 over x squared plus x minus 2 to simply equal x minus 3 over x minus 1. But note that is only if x does not equal negative 2. If x equals negative 2, note that the expression on the left is undefined because of the 0 denominator. The expression on the right, it really doesn't care about when x equals negative 2 in terms of continuity. It would be defined there. The only value that makes the expression on the right's denominator 0 is 1. So that would be a shared point of discontinuity between these two functions, but they're not equivalent because they have different domains. Again, the expression on the right-hand side includes the value x equals negative 2, whereas the more complex version on the left has a different domain. It does not include that value x equals negative 2. Another example of this, I'll breeze through this one. X plus 3 is the simplest form of that expression, but x plus 3 and that expression are not equivalent. They don't have the same domain. Note the domain of x plus 3 is all real numbers. There are no points of discontinuity, but the domain of this other expression in this case it does have a point of discontinuity at negative 2, meaning that value is not in its domain. Example problem number 1, simplifying a rational expression. The question is, what is this expression in simplest form? State any restrictions on the variable. So that's important. We'll take careful note of that in just a moment. So first we factor the numerator and denominator. Good thing we've been reviewing factoring. We cancel out the binomial x plus 2 to find x plus 5 over x minus 5. However, there were some restrictions. Pay very careful attention. Before we canceled, we had the restriction that x cannot equal 5 and x cannot equal negative 2. Those are the two values that would make our original expression have a denominator of 0 and so therefore be undefined. Those values are not part of its domain. So basically that's what it says here below. The simplified form is x plus 5 over x minus 5 for x does not equal 5 and x does not equal negative 2. On your work, it's absolutely fine with me if you would write something like this as x cannot equal 5 comma negative 2 instead of writing them separately. Very good thing to take note of. If you were to do the simplification and then only look at the simplified version, you would miss out on one of these restrictions. In the case of the simplified version, you'd only find the restriction of 5 because 5 minus 5 equals 0. And you would miss out on the negative 2 restriction because it's been canceled out. So be very careful. Always go back to the original expression, or at least its factored form, when finding restrictions on the domain. And the moment you've been waiting for, your chance to prove that you have got it. Even though I've been trying to pick up the pace on this video, keep the videos a little bit shorter, I would like to take a moment to discuss this problem in a little bit more detail. I won't give you the answer, but I want to help you get started because I feel this one's a little bit different from the example problem and in a way you may not remember from Algebra 1. So here's the exploded version. Note the prime factorization of 24. Often we've used factor trees and then we just look at the very ends of the roots or branches. It would be 2 times 2 times 2 times 3. Right? Those are the prime numbers that when multiplied, 2 times 2 times 2 is 8, times 3 is 24, and then x cubed is simply x times x times x, y squared is y times y, and you can see I've done something similar with the denominator. It probably looks familiar now. You probably remember doing things like this in the past, but here's what we're going to do is we'll reduce this by canceling out pairs of values from the numerator and denominator. A lot like playing Go Fish. It's as though the numerator says to the denominator, do you have any y's? And the denominator gives up one of its y's. And then it asks for another y. Basically, we're pairing these up. If you don't like Go Fish, you could think of it as folding socks. We're finding pairs that match, and we are identifying those. This one's kind of a tricky one to watch out for. I don't want to circle that negative sign. I think you'll see why in just a moment if you don't already. And I also see a 3. That sock was stuck at the bottom of the hamper, but we didn't miss it. Got it. Oh, and then I don't got it. And then with the redo button, I've got it again. So these things are going to cancel out, right? And that's really what's going on when we reduce fractions. And so what we'll have left are, well, the things that we see here that are left. 2 times 2 is 4, right? You see where the 2 and the 2 came from. X times x is x squared. The y is completely canceled out. And then on in the denominator, I still see a negative sign, right? I was careful not to cancel that out. So it will be a negative still. X times y. Oh, now that I'm doing this, I see that I've missed some socks. I would be a bad Go Fish partner. It looks like I did have an X and said no. Anyhow, we do have some more things to cancel, and this was good. I started writing the problem and saw that, well, I missed something. So instead of, well, I'm going to take this just one step farther instead of going back and starting over. I'm going to cancel out the x and the squared. So we still have 4x over negative y. Oh, I feel like I have gone too far. I'm giving you too much of the answer. But that's all right. I think this was worthwhile. I also want to show you, now that you've seen this, the method that we would typically use to reduce this fraction without going through all the trouble of exploding it or writing it in expanded form or prime in terms of its prime numbers. So 24 and 6, we just reduce that as though it were its own fraction. 24 over 6, and in this case negative 6. Well, that's going to be negative 4, right? Negative 4. X cubed over x squared. Both of those will cancel out, and so will 2 of the 3, right? The x cubed. 2 of those x's will cancel out, leaving just 1 in the numerator. So the most common way to do that, that's simple, is just to cross out the 3 but leave the x. So that would be negative 4x. And then we have a y squared over a y cubed. So this y squared completely cancels out. Y cubed becomes just plain old y, but that's in the denominator. So y. As long as you understand how to do this, that's much faster and easier than writing it in an exploded or expanded notation. And in terms of restrictions, just consider back to the original expression and find any values of x and y that would lead to a 0 denominator. Pretend you don't remember what I just did and make your selection from the choices below. And got it, question 2 of 3. Make your selection from the choices below. Got it, question 3 of 3. Make your selection from the choices below.